In this lesson, we're going to be talking about scientific notation, which means we're going to be converting between standard numbers to scientific numbers, and we'll be using scientific notation in some math problems.
Scientific notation is a way that scientists easily handle very large numbers or very small numbers. And since we're talking about chemistry, we deal with very large numbers and very, very small numbers, like this lovely example, which I will not read for you. But you can easily write it and read it as 5.6 times 10 to the negative 9th.
So when we look at some scientific numbers and some standard numbers, let's talk about the subatomic particles that make up an atom, because those things already are very tiny. We're noticing with a proton in scientific notation, you can write it as 1.67 times 10 to the negative 24th grams. If you were to actually write that out accurately, it would require all of those zeros. Same thing for neutrons, and even more zeros for electrons. You'll notice, though, that there's a difference of 4 zeros in the differences between protons or neutrons with electrons.
So here's an example of how to write scientific notation. Here's 1.6726 times 10 to the negative 24th grams. Okay, so coefficients are the first portion of a scientific notated number. They consist of a value between 1 and 9. It has to be between these values. It can never be a double digit, so you'll never get 10 point something.
And they can never be 0 point anything.
Right. And then you're always going to have a power of 10 value after it with a negative or positive exponent. When you have positive exponents, that means the number is much larger than it appears as a coefficient. When you have a negative exponent, that means the number is much smaller than what it appears as a coefficient. And then you are followed finally by the metric unit.
So when we're converting from standard numbers to scientific numbers, if you have a number that is larger than 10, you're going to be moving the decimal place to the left.
Say it one more time.
So for example, if you have this massive number, which is Avogadro's number, which we'll be talking about later on in the year, it is in everybody's class. If you have that many atoms, which is a gigantic number in the millions, billions, trillions, quadrillions, I don't even know, you can simplify it by writing it into scientific notation. So the first thing is you locate where the decimal is. It's all the way down there. Then you count the number of places to the left until only one digit remains. Therefore, if you count them out correctly, your number should be 6.022 times 10 to the 23rd atoms. Again, that's a very big number, and that is why there is a positive exponent.
The times 10 factor is always going to be a placeholding factor. So now for very small numbers, numbers less than 1, you're going to move the decimal to the right. So numbers of decimal places moved is equal to the exponent number, but as a negative value. So if we look at this example, we first have to locate the decimal, which is all the way to the left, then count how many zeros there are until we reach the first value, the first significant figure, and include that in your count. So this lovely number becomes 1.6726 times 10 to the negative 24th grams.
When we're converting from scientific notation to standard, it's pretty easy. To change a number from scientific notation to standard form, you move the decimal point to the left if the exponent of 10 is a negative number, or to the right if the exponent is positive. You should move the point as many times as the exponent indicates. Do not write the power of 10 anymore.
Remember, large numbers are going to have a positive exponent. Negative exponents are going to be very small numbers.
So let's try these two examples. First, we have 5.34, and it's being multiplied by 10 to the positive third power. As Ms. Diamantopoulos just said, if you have a positive exponent, that will be a large number. The second problem looks almost identical, but now you have 5.34 times 10 to the negative third. That negative 3 exponent means it's going to be very small. Pause the video right now and try these two problems. So when you do the math, you'll notice you're going to be moving the decimal place on your first example to the right. You're going to go 1, 2, and then 3 places over, which gives you 5,340.
Notice that you put a 0 for the extra space.
Making it a larger number. For the second problem, you notice you have 0.00534, which means it's a very small number based off of the fact you have that -3. Because of that -3, you're moving the decimal place to the left, and that means you take that decimal and go 1, 2, 3 places to the left. Draw your decimal, add your 0, and then fill in the gaps with the other zeros. You'll notice both numbers are now similar.